Hello, I'm Yaron. I'm co-founder and CTO of Iguazio, an MLOps platform company. Iguazio is actually one of the co-founding members of Aya. And what we're going to discuss today about is how to automate and scale experiment tracking in production. In general, we're going to speak about production pipelines and also how specifically it relates to tracking of various artifacts and experiments. Before we dive into understanding how to do it right in production, let's understand the different steps, what we need to do, and how does it work today. So today, most organizations, when they build machine learning products or solutions, they have a more of a iterative or interactive flow of building the model. What does it mean? It means that you have data lying somewhere, whether it's in a data lake, some files, or data warehouse. You take that data and you make some data preparations, join, group, filter, aggregate, and so on. Once you have a basic data set for training, you run training. The training could be done using automated tools on cloud services or writing your own code, some scikit-learn function or TensorFlow and so on. Once you've trained the model, you run evaluation. You want to check with the bigger data set that your model actually behaves, maybe apply different data patterns to see that your model is also resilient. And when you finish this overall flow, you generate a model. In many organizations, just throw it out to a different group that will take that model, put it behind some API, and serve the data. But this is a very interactive flow, where in reality we have in production we rather deploy things in a more automated fashion using CI. Sometimes we train at scale. We don't always use Jupyter, and we're going to see the shift. So in this environment where we train interactively, etc., there are many different tools to track the experiments and make comparisons. So why do we really need experiment tracking? Initially, it started with two main reasons. We want to be able to run different parameter sets, different inputs, and compare across different runs. This run was better because it's using different parameters. If we'll repeat the same parameters, the same data, the same code, we're probably going to get to that same result. So that's the first reason people started with experiment tracking. The second was around it's a tool for developing your models. You want to have different features. You want to see which features has better impact on your model. You want to be able to do visual comparisons to look into sensitivity of data features or parameters and so on. So there are many good tools. You can see some snapshots here of different frameworks that are geared towards allowing you to run interactive experiments, visualize those, compare, and so on. But in reality, when we are going to deploy machine learning into real production world, it doesn't really look the same. It's not Jupyter notebooks that you run interactively. There's a lot more to it to building a machine learning project. And we could see those different disciplines and then in many organizations are actually done by different people, different teams. So first we have all the aspects of data gathering. Data gathering in many cases is not manual. You're not getting an Excel spreadsheet. Data is arriving from operational systems, from APIs, from message queues, from streaming, from operational databases, from data warehouses, etc. And that data needs to be processed online. It's not being processed, by doing a shift enter on your Jupyter cell. There may be an analytic system or Spark or Flink or other analytic engines that will process the data for you. And even in the training that we've looked in flow that we've looked into before, it doesn't necessarily run again as a single notebook or a code in PyCharm. It may actually run at a bigger scale with lots of different data sets or bigger data sets that run on top of a cluster, like a Kubernetes cluster working against a distributed database. There are many ways of creating parallelism for training itself using technologies like Dask or Horvath or Spark or other frameworks. We can essentially distribute our training. So the same practices that we've used in an interactive flow using Jupyter may not necessarily apply into the production side, because here in production we want to have everything distributed, containerized, work with a lot more data, microservice oriented. Every time we build something, we want those artifacts to be fed into sort of a next step in a pipeline. When we generate models, we don't just want to generate a file and list it. We want to generate a model object that could be used and deployed into production sites. So we may need to add to that model additional metadata and information. And also, when we serve model, it doesn't end with an endpoint. It's not just like putting an HTTP endpoint that serves our incoming data. In many cases, the models need to first interact with some API. There is some JSON request that arrives, need to get a response. That JSON request may not have all the details, like it has a user ID, so we need to go against some database, real-time database or in-memory or NoSQL database, and enrich that request, that user ID, with all the information about that user. And then we may want to do serving of the model itself. Once we've done the serving, we may need to take the result and maybe push it into a database or a message queue, or run additional steps of data validation. So, just building an endpoint behind the REST API will not really provide us the required results. And the last thing is monitoring. We don't want to just monitor the aspects of training and artifacts in the experiments. We want to also compare and see what's going on in production. And experiment tracking has a lot to do also with production data, because, for example, if I'm doing something like drift analysis or accuracy analysis of the production data, where does all the statistics that we compare with come from? It essentially comes from the training process. Okay, when we're doing the training and the testing of our models in the development, we can store all the information about our data, our features, our statistics, and then in production, we essentially compare that with the production data, and this way we know if we have a drift. So that means that the artifacts and that we generate throughout the training, it doesn't only need to be visualized and seen in a nice fancy UI. Also it's a working tool that needs to be used in the production. So it needs to have metadata and needs to be stored in a way it's easy to access, and so on. So what we've seen that execution tracking, I won't call it experiment tracking because it's essentially tracking what we're running, is not just for visualization, that essentially this is really where it started. There are additional applications for all this data and metadata and artifacts that we're generating in our experiments, okay? And those are some examples. For example, if we want to run AutoML or hyperparameter tuning, the fact that we can inject parameters and measure the outputs allows us to create a feedback loop and run loops. So essentially run over and over and over until we get the best results. There are other aspects in machine learning that are more around the legal aspects, data governance, explainability, approval processes. When you build a model, you want to be able to prove that you've done everything right in your training. So again, you won't do that for visualization. You need to have automation. You need to have automated approval processes. You need to have forensics. People need to be able to look back in time to see how you trained and why you trained data and so on. Another reason for tracking all the data is when you build pipelines, multi-stage pipeline, let's assume you're building data preparation and then training and then testing, etc. If you log artifacts in each one of those steps, you can essentially build a pipeline where one step uses artifacts from the previous steps. There are other aspects of, research usage, profiling. You're debugging some TensorFlow model. You want to know which layer generates, takes the most amount of GPUs. Maybe there are ways to optimize and reduce the CPU and GPU consumption. And there are other aspects of, for example, when you're logging a model, you may want to incorporate additional metadata and functionality like schemas and statistical information, etc., about the training process. And this will be used for the serving layer to essentially avoid the need to go and configure manually and add your own metadata in the process. Essentially, you want to make things glueless, so you do less work and you get more robust solutions. So essentially, if we're looking into what is execution tracking, what are we tracking and how are we tracking it? So the general idea across all the different frameworks is sort of the same. You have an execution environment, let's call it. Essentially, it could be a process or it could be a container, whatever. that's running. This execution environment has code. The code also has packages. The packages, all that is running on a OS or certain Python version. And this is also using resources. So this is something we need to track. We have to know what's the code, where's the code coming from, which packages we're using, because if we're using scikit-learn version 1 or 2, then it may impact the behavior of our experiments. And now we have inputs. The inputs into such a process will be things like labels. We may want to label every run, parameters, secret credentials code. We do need to run this code with some resources that may need to be protected. And data inputs, like a data set that we want to train on, or a data set that we want to manipulate and generate a new data set from, and so on. So we have, those are the inputs to our execution, and those are the outputs of the execution. So on one end could be results could be numeric values, could be plots, charts, and so on. We have operational data like logs, telemetry data, CPU utilization, GPU usage, profilers, and so on. And we have data artifacts. So that's in general the way that all those systems work. And remember, we have to track all of those things every time we run. We need to track the inputs, we need to track the execution environment, and we need to track the outputs. Now, as I mentioned before, we may actually have in our tracking process multiple steps. It doesn't end with just doing training and that's it. Because when I'm running a machine learning pipeline, usually I will take some incoming data snapshot from the production data. Usually, these days you're doing it with the feature store. So the feature store allows you to create production data snapshot as an offline feature vector. And then I want to take code and parameters for my machine learning pipeline, or maybe even trigger all of that process every time I change code in a Git or every time I create a new data set. The first step is usually doing data preparation and then doing training and validation. In some cases, we're doing model optimizations. We may do the deployment, and each of those steps needs to be monitored. And in some cases, we're actually passing parameters and artifacts from one step to another. For example, we're doing data preparation. We take the data, we push it into the training. So we need to be able to monitor not only a single step, but something which is distributed. And also there is a feedback loop. So the monitoring of the actual deployment of the actual models, monitoring drift and accuracy and statistical behavior and even the data itself essentially needs to feed back into the same feature store, so we can essentially do a retraining process with fresh data. Or maybe as a data scientist, we want to be able to analyze production data and figure out maybe there's certain features that we've overestimated or underestimated. Okay, and what it also means that because we're building pipelines where we essentially move artifacts around, we move models, we move data sets, we move parameters around, we need to have a common metadata and common APIs to access those. So if we're building a training function or a data preparation function or a serving function, they all need to speak the same dialect. And we don't just want to speak files, because we also have metadata that needs to be incorporated in all those different objects. Okay, and some other challenges when you're building all of that is the first, then when we want to do tracking, in many cases we add code. You can see some snapshots of examples. In many cases, in order to have parameters going into our code, we have to start working with all those arguments and so on. We want to log parameters, matrix, data sets, and so on in our code. Here's an MLflow example. You add all those logging hooks within your code, so that's a headache. And there are additional production requirements or challenges. Like first, you want to build everything in a more automated and agile flow, pretty much like around CI/CD and using Git as a reporting system and so on. So that means that if I have something interactive with very nice UI and all of that, but it doesn't know how to work within a Git context, maybe reporting to the Git pull request, as I'm going to show you in a minute, it may be nice, but not necessarily solving my operational problem. Other challenges, in many cases, the training or some of the other functionality is running distributed. So if we're tracking something within our process, if this thing runs within a single process, but my job is actually running on a dozen processes, how do I really track the combined results? And also in many cases we're working with data, and when we work with data, especially in the cloud, or using different, maybe we're training on our laptop using a local file system. Now when we're training on a container over Kubernetes, we're using S3 object storage as a source of data. Do we want to put code inside our functions to take care of this sort of duality that sometimes I use files, sometimes I use external API, maybe I'm using BigQuery as a data source, or we want to have some abstractions for that. And also we want to record operational data and metadata, not just experiment, like, what was the OS version that we're running on? How much CPU was used? What kind of configurations we were using on the system that we're running, and so on. This operational information may also helps us find issues or understand why our code behaves in a certain way, and we want that operational data and metadata to be collected automatically. No one wants to start adding logging code, to handle all of that. There are aspects of security, obviously. You're generating artifact by one job, and then another job is reading it. Does the other job has access credentials to get into that data? And another major problem that we're seeing is what do you do with versioning? We can version individual experiments, but how do we version things across, the data processing, the training, the serving, testing, and so on. So we need to have ability to create tagging and labeling and versioning across multiple stages or multiple types of workloads. So those are different challenges, and some of the things that we're doing in Iguazio, we're building several open source frameworks. The most popular ones are Nucleo with 4,000 or more stars in GitHub. It's a serverless engine, and the MLRun is essentially a layer of orchestration built on top of Nucleo and other frameworks specifically focused on MLOps. And we're going to see how those tools are helping in this flow. So the first thing that we did after working with so many products that are being taken to production and operationalized, we said, how do we build a production first mindset? So instead of looking into we're going to do experiments and all that, and then we're going to find a way to go to production, let's first define how a production pipeline looks like, and then take backwards and see what are the different requirements we need to do in development in order to get into that state. So when we're analyzing the production pipeline, usually has four major components. The first component is essentially analyzing and preparing the data, and this is done today with feature stores. So MLRun has a very powerful feature store built in. This next thing that we want to build is a sort of think of it as machine learning CI/CD flow. This is really where you're building the models. You have a machine learning pipeline, intercepts a piece of data, runs training, evaluation, testing, and so on, and then generates an outcome, which is a model and a set of artifacts that go along with it. The third piece is building those application pipelines that know how to intercept user requests, contrast them with the model and reach data from a feature store, and so on. So those are multi-stage real-time pipelines for building those intelligent applications. And the last piece is ability to essentially track all this telemetry, all this information, do real-time analytics on that to identify accuracy problems, drift problems, business matrix measurement, and so on, and real user data, and take all that data and put it back into the feature store. So then, we can retrain and all that based on fresh data. So essentially, we have four components. All of those components have built-in tracking into them, so you don't need to do a lot of coding. Each one of those has self-reporting and self-tracking for the individual's discipline. Like for the model serving, you have model monitoring and things like drift and accuracy analysis. For training monitoring, you'll have all the aspects of artifact tracking and so on. So this is the operational layer, and through APIs and SDK, some of them I'll show in a minute, you can work with any other tool in the ecosystem, whether it's with IDs and notebooks and PyCharm and Jupyter, or BI tools for exploring data, AutoML frameworks like SageMaker, AzureML, DataRobot, etc. CI frameworks, Jenkins, GitHub Actions, and so on. So there are APIs to handle all of those different frameworks. And also you can potentially use third-party experiment tracking solution, and I'll show some of those examples as well. The base concept around MLRun and all the different services that MLRun provides, from the feature store and real-time serving and training and so on, is the concept of serverless functions. And this, if you looked at my previous slide about how do we do tracking, serverless computing essentially helps us do the tracking in an automated fashion. So the general idea in MLRun that you have about 7 different options of serverless functions, depending on the use case, like Spark and Dask and Nucleo for real time, and so on. And those can essentially take a piece of code along with packages, images, and other things, and OS requirements. Then how to take that code and deploy an auto-scaling service. So MLRun functions essentially scale horizontally in a seamless fashion. You can specify a list of resources, like how much CPU and GPU you want, but again, it's also auto-scaling, so it will fit the use of resources based on the demand. And it will essentially create a sandbox around your code that tracks everything that goes in and everything that goes out. So all those tags, parameters, data, objects, etc. It also has a data abstraction layer for data movement, that when you write your code, you don't really care if it's in S3 or Azure Blob Store or NFS or local file system. It knows automatically how to connect to the different data sources, so you don't need to change your code. At production time, you could say, this time I'm reading from S3, or I'm debugging stuff, I'll just use a local file. So this is the general idea. And the way that it's helping us, if you're looking at the traditional process of machine learning, we used to have more of a siloed flow where someone is doing development on his own laptop or notebook. When he finishes, is going to the ML engineer, which is building those machine learning services are on top of Kubernetes, essentially building containers, YAML files, in services, and so on. And when you want to compose something more as a flow, you need to take those different steps and combine them into a full workflow. You have workflows for data engineering, for training, workflows for the production. So that's another additional work that someone needs to build all those sort of pipelines. And finally, you collect all the telemetry in different systems, but sometimes you lose the context of the telemetry, because the telemetry is just generic, Prometheus, and so on. You don't really understand what you're measuring, so you can't build a feedback loop around your deployment. With the MLRun way, it's slightly different. It's essentially you take the code. I'll show it. One line of code. You convert your code along with its requirements and other aspects into a full microservice that runs. No need to do any DevOps work, any development work. And this service is robust. It's auto-scaling. It's secure. And so on. And when you want to compose something bigger, like a multi-stage pipeline, you just drag and drop a bunch of functions from either the marketplace or your own custom-built functions, build those pipelines, then deploy the pipeline as a whole. And because all those serverless engines essentially collect the telemetry automatically, that means, and also they collect it within the context. So if you're using the model serving function engine, it collects information that are very relevant for model serving, along with the model details, telemetry, and so on. So then when we have all those connected without writing any additional code, you get very detailed, very high level monitoring data that could be used for example, for retraining the model, or for the developer to essentially examine what's going on with the real world data. And this is accelerating the deployment of new projects significantly throughout all the ones that used it. So again, we have 4 major components. I'm going to dive quickly into each one of them, and then I'll focus more on the aspects of tracking. So one is the feature store, which is the ability to build features automatically for real-time and offline. The second piece is the real-time serving pipeline, where you compose real-time pipelines, for data collection, for API integrations, for model serving, ensembles, and so on. Building the feedback loop and monitoring layer, and finally the automated flow for building your models. The first piece is the feature store. This is where you can essentially connect to all types of the data sources, different object store, data warehouses, BigQuery, Snowflake, video feeds, images, and so on, using different engines, real-time or batch. You can build transformation pipelines that prepare the data, and then once you have the features in the catalog, you can serve them to all those different applications, whether it's for data exploration, from your notebook and pandas. There's also a Spark plugin. You can run training based off a snapshot of data from the feature store. You could do the serving using real-time APIs of the feature store. And the model monitoring works in a very interactive way. With the feature store, on one end, it's using the statistical information stored in the feature store to do analysis like data quality validations, accuracy, monitoring, drift, and so on. But also all the production data is going back into the feature store as sort of production feature sets, as we call them. And you can see this is just an example of the feature store UI in MLRun, that you can essentially build transformation pipeline and persist the data in real time and batch. What's very unique about MLRun and those serverless engines that serve underneath, that they can process any type of data. It's not limited like Spark or Flink to structured data. There are different examples in the MLRun demos for doing NLP analysis, document processing, video processing, and so on. And essentially what you can build with MLRun, and this is using the same serverless functions, is real-time pipelines. This is an example of real-time pipeline that has, ingesting data and then doing enrichment, pre-processing, running ensemble across models, and post-processing. All this stuff is written by a dozen or two dozens of line of code. There's a full demo in the MLRun tutorials and MLRun demo repository for building various such pipelines. So you can build those pipelines in a very easy way, and then you just turn on a simulator for this entire pipeline in your notebook or ID. You can run the simulator using events. And finally, when it all works, you do deployment. When you do the deployment, essentially all the telemetry, all the tracking across all of those components is turned on, and you can see the results in Grafana or the MLRun UI. And this is an example within the MLRun UI to track all this information, which is more real-time on the production site. And some of this real-time information also has to do with the experiment tracking, because it's using the experiment tracking artifacts and comparing the information from those with the real-time data that's being intercepted. The fourth component is very relevant to experiment tracking, is the pipeline automation of MLRun. So there are different pipeline tools. There's Kubeflow, there's GitHub Actions, etc. It's not replacing those. It's actually a layer on top. So MLRun knows how to execute Kubeflow or GitHub Actions or GitLab or Jenkins and build workflows, machine learning workflows on top of those. Many of those don't have the built-in capabilities of doing data processing, logging artifacts and models, and building those serverless functions, etc. So with MLRun, essentially you have all those different functions. Those functions could be taken from the MLRun marketplace, or you can build them yourself. You can build those pipelines that get triggered by either like a CI event, a schedule event, an API event, and so on, and track all those pipelines as a whole. And we're going to look into that. But the nice idea is that you can also track it not just within the MLRun system. You can export the tracking data to operational systems, like in this case, GitHub user interface. Okay. And all of those different steps are elastic. Each one of them can horizontally scale out. So that means you can deal with very large scale data and machine learning processing. How do you essentially turn on tracking within your code running in MLRun? Those are some new tricks from the recent versions of MLRun. And I've seen also other companies are essentially coming with the concept of auto logging. I don't want to tell you what to log. I want you to just log whatever you think. And it's not just logging for the sake of experiments. There's also a lot of logging here for the sake of operationalizing your work. So in MLRun, you can just go and build your own simple function. No need to build arguments and all of that. MLRun will analyze your code, will detect the parameters, will build documentation for your functions and so on, just by um, doing importing your functions. And those auto logging capabilities, essentially, you just add a single line to your code where you wrap the model object and you can provide some other parameters. The reason we're providing the data is because we want to do things like accuracy measurement. We want to know, take the test data and take the model and take the production data and take the training data and build the evaluation and testing and different matrix of our model. So this is the single line that you add. And what this line does is essentially does all the logging, logs artifacts, matrix, handles data lineage, which data is used when and the versioning of the data. It handles auto scaling, so it generates hooks underneath for scaling the workload, for example, on top of Horvath for deep learning. It supports all the things required for pipeline, for essentially using it in Kubeflow and in other places. Resource optimizations like GPU optimizations and so on, checkpointing, integration with a different exporting mechanism, like it knows how to export data into TensorBoard without writing a single line of code. CPU, GPU profiling, you want to analyze your layers in deep learning with GPU utilization. You don't need to write any piece of code. And there are a bunch of other things that exist today, and we're building and enhancing it all the time. So the general idea is that as a data scientist, you just add one line of code, no need for instrumentation from that point onwards. All that is happening automatically. How to use that function? It's relatively easy in MLRun. You just say, I want to take this file that I've seen before. It also requires some image, maybe some package requirements. It's running as a type job. There are different kinds like Spark and Dask and Nucleo and others. Job is sort of the basic container in Kubernetes option. So I just want to take my code and turn it into a serverless function, essentially a service that every time I'm going to execute it, actually doesn't necessarily run locally. It can run on the cluster distributed. There's actually a flag that you can turn on run locally. So you can, if you want to debug it locally, you just turn on a flag, run it. When you feel it's ready, you run it on the cluster in a scale out fashion, or you run it within a pipeline like Kubeflow or others. So first thing we need to do is create a function, and then we can just run the function. This is an example of a data generation function from the tutorials. I can just run a function. Function run is an object that has all the information, all the artifacts, all the details about the run, status logs. So I can actually use the output of one step as an input of another step. So now I want to take my trainer function and execute it with different inputs and different parameters. All the data movement is going to be handled automatically behind the scenes. The parameters are going to be pushed into my functions appropriately, and all the results are going to be tracked by this object. We can also use hyperparameters. This is the simple way. There's a more advanced way of also you can specify the type of hyperparameter, grid, list, random, early stop. You can distribute the hyperparameter runs across multiple containers. So this is more advanced, but this one is the basic option. Just give me the different parameter combinations, and MLRun will run a bunch of child executions with the same function every time, different permutations. And those objects, for example, this trainer run output essentially generates automatically all those different matrix and a bunch of artifacts, that are generated without adding a single line of code. The other thing is that this tracking is not sort of closed just to MLRun itself. MLRun has plugins to report into many different systems. So if you like to go and see your progress on Jupyter, the progress of your pipeline and all the artifact results and everything will be shown on your Jupyter as a result. If you need something more detailed, you could zoom into MLRun UI and you could see the progress, the logs, all the resource information, the artifacts visually, and so on. If you're part of a CI flow that you want to trigger your pipeline and record the result as part of the pull request, it will automatically report into GitHub or GitLab, depending on what you're using. It knows how to figure out it's running within the CI system and know how to write into the GitHub or GitLab API and report. So this way, every time you're executing, you're changing code, you're running the training again. You want to know what was the result from that execution. So if you're using something visual like weights and biases or others, you don't have this integration into the pull request. You don't see the results after the fact. So here, if you're triggering the training, you can actually see in the pull result, all the results, the accuracy. You have a URL link into the MLRun UI that opens a much more detailed view, and this way you can have someone approve it in an easier way. Again, we mentioned it knows how to export into TensorBoard and works with Kubeflow, even Slack and other mechanism. And MLRun is open source, so you could just add your own plugin for what we call notifications. Okay, now when we're building something more complete, and we want to look into the overall flow of how to deliver something from development to production, we can follow this example, which is something we're using across multiple customers and deployments. The first flow is someone is developing a feature. Maybe you're building a training function, or maybe you're enhancing the training function. So you create a branch, create a feature branch. And this is where, even in the feature branch, you need to do some data preparation, maybe some training. Once you've done the training, you want to build a model and do some predictions, verify that it's working. Sometimes you want to do tests on the model, simulate the model, the real model, and see that it's actually working, not just the model is working, but also sort of the data preparation in the model, pre-processing, post-processing actually works. So you can run this interactively in your local process, in your ID environment, without having a cluster. You can run it on top of a cluster by just connecting to an external Kubernetes cluster. And at a certain point, you feel it's ready, you just want to push it into a development branch. When you push it into development branch, you want automated testing. So there are some static tests like Black and Flake 8 and linting and maybe some other unit testing that will run automatically every time you create a pull request. Once you've done that, then you want to run at scale. So this ability to plug data and change the data from development to production by just plugging a different type of data source is powerful, because here we may use some CSV file. Here we may actually go and work against S3 or BigQuery or some other large data warehouse. And maybe this time we want to scale out our training across 5 virtual machines, and here we're just using our local CPU. Maybe here we want to run over GPUs to make it faster. So you could just use the same function, just with different parameters for resources and data and so on, and run this. And the reporting will happen directly into your pull request or other systems. And once you see this reporting and this is what you've expected, you would approve the merge based on the results of those testing and the results of artifacts of the training. And once it's there, you may have additional regression tests and so on. So this is building in the staging environment. You build a new version. At a certain point, you want to put things in real production. So you essentially merge the development into the master. The first thing that happens is you want to try the deployment, try the new tool, the new building blocks, the new model surveying, the new data preparation code, and so on a canary. You want to build it on, let's say, only 10% of the data, the user data, will go into the new model. Once you've seen the results and you validated that it actually works on sort of a sample of data, then you could approve moving from a canary deployment to a full deployment. And this is essentially you're tagging, you're creating a release, and it will do automatically rolling upgrade of your production data. And what's cool about MLRun, because it addresses the data portion and the serving portion, you can actually do rolling upgrade of the data preparation and serving as one version, because the versioning is cross components. It's not just on an individual component of the pipeline. So if you want to learn more about MLRun, and there's a very nice set of tutorials now in Katacoda, which work locally without a Kubernetes cluster, or there's instructions how to install MLRun on a Kubernetes cluster, or if you don't want to avoid the hassle, you could use Iguazio's managed service and just access it remotely or from within the platform. So I recommend going through those tutorials. There's lots of documentation in MLRun around all the different things that I mentioned, and there's a bunch of demos in different disciplines, machine learning, deep learning, and so on. So those demos are complete. They have the feature engineering aspect, the training aspect, the serving aspect, again, NLP, deep learning, machine learning, and so on. So feel free to go and look into those, and I hope I help giving you some new perspectives on how to operationalize your machine learning. Feel free to contact me over LinkedIn or Twitter or email. And thank you very much for listening.